atmospheric conditions. Watch them streaming back from the nose of this missile. There. This time, we're going to hold the picture still for a few seconds. Let us see a shock wave form again in the wind tunnel. A diagram shows what happens. At the critical Mach number, there is a point on the wing where m equals 1. At higher speeds, the point grows into an area in which the flow is supersonic. That is, where m is greater than 1. Outside this area, the flow is still subsonic. m is less than 1. The rear boundary of the area is the shock wave itself. As the aircraft accelerates, so the area of supersonic flow increases, and the shock wave moves back, growing larger and stronger. A shock wave at right angles to the airstream is the means by which the airflow suddenly decelerates from supersonic to subsonic speed. How are shock waves formed? On the rear part of the wing, every point, such as this one, sends out innumerable tiny pressure waves at the speed of sound. In the forward direction, these waves meet airflow in the opposite direction and make less and less progress until they reach a stage where they can't travel any further forward because the airflow itself is moving backwards supersonically. It's like trying to step off an escalator going the wrong way. The pressure waves constantly pile up here, and this is the shock wave. A shock wave is a very narrow region, about 1/10,000th of an inch thick. Across this region, the supersonic airflow is violently reduced to subsonic speeds. Much of the air's energy of movement, or kinetic energy, is dissipated as heat. The temperature of the air rises suddenly as it passes through the shock wave. There is also a sudden rise in pressure. The energy wasted as heat in the shock wave must be continuously supplied by the engine. Otherwise, the aircraft would decelerate. So as the aircraft approaches the speed of sound, it meets an additional kind of drag called wave drag. Wave drag is a large proportion of total drag at transonic speeds. As the speed of airflow is increased still further, the region of supersonic flow goes on growing larger, and a second supersonic region starts to form on the lower surface of the wing with another shock wave. At speeds approaching the speed of sound, the most important result of the shock wave is to cause the airflow to separate from the wing surface. This is called shock-induced separation. It produces a large turbulent wake, which alters the pressure distribution. Lift is reduced, and the turbulence creates drag. In this aircraft, the turbulence strikes the tailplane, causes violent buffeting, and so limits its speed. Other aircraft experience such serious troubles as sudden loss of stability and reduced effectiveness of the controls. We can't see separation in flight, but this aircraft has wool tufts stuck on the wings. They lie flush when the airflow is smooth and flat when shock-induced separation occurs. But shock waves don't only appear on wings. Speed up of the airflow occurs around the canopy and many other parts of the aircraft. Wherever it's great enough, there shock waves will form. Shock waves cause a vast increase in drag and may cause serious control troubles. One way of avoiding these troubles is to put them off to still higher speeds by raising the aircraft's critical Mach number. There are two chief design methods for doing this. The first is to use relatively thin wings, that is, wing sections with maximum thickness small compared with width or chord. Thin wings, in this sense, can of course be very deep. The thinner the wing, the less the air is speeded up, and so the critical Mach number is raised. These two wings are of the same general shape and of the same angle of incidence. The tunnel speed is the same for each. As it increases, the shock wave forms on the thicker wing at a Mach number of 0.8, but not a sign yet on the thinner one. Here it comes at last, at a Mach number of 0.9. But wings can't be made too thin or the landing speed would be too high. The other important way of raising the critical Mach number is by the use of sweepback. To understand this, let's look from above at the flow over a wing. The contour of the wing section determines the amount the air is speeded up. Now, sweep the wing back. We can represent the velocity of the airflow ahead of the wing by an arrow of a certain length. We can consider this velocity as made up of two smaller components. A yellow component at right angles to the leading edge, and a red component parallel to the leading edge. The red component can be considered to flow along the span and is not speeded up by the wing section. But the yellow component flows across the section and is speeded up by it. It is therefore only this component which affects the wing's critical Mach number. So the maximum speed reached over the swept wing will be less than it would be over a similar straight wing. In particular, if the flow over the straight wing has reached the speed of sound, at the same flight speed, the flow over the swept wing will still be subsonic. The swept wing has, therefore, a higher M crit. The greater the sweepback, the more the critical Mach number is raised. For instance, suppose the straight wing has a critical Mach number of 0.8. By sweeping the wing back to 35 degrees, the M crit is raised to 0.98. But this is only the theoretical result for an infinitely long wing. In practice, the critical Mach number would only be raised to about 0.9. Sweepback, like thin wings, brings its own problems at low speed, such as tip stalling. So designers must compromise between high speed and low speed requirements. Aircraft designed to fly near the speed of sound use thin wings together with sweepback to obtain a high critical Mach number. Various arrangements have been adopted, all very different in appearance. If the swept wing is too thin to contain the engines, they can be mounted externally in pods. Alternatively, the engines can be buried in the wing roots, which are more highly swept than the remainder of the wing. special kind of sweepback is the crescent wing. Here, the sweepback is reduced in stages to avoid tip stalling. The delta wing combines a high degree of sweepback and great strength. The Delta's large wing area makes it very maneuverable and gives it a good performance at high altitudes. The simple Delta shape can have many variations. Some Deltas have a tailplane to improve maneuverability at the expense of slight extra drag. Today, aircraft are being designed to fly at speeds far above their critical Mach numbers. Problems of extra drag and loss of control caused by shock waves are being overcome. But for many years ahead, airlines will cruise below their critical Mach numbers.